Alrighty, let's finish up this chapter. Let's do it. Motivated to get away from the list hell. Okay, de-entry cache. After the VFS layer goes through the trouble of resolving each element in a path name into a de-entry object and arriving at the end of the path, it would be quite wasteful to throw away all that work. Instead, the kernel caches de-entry objects in the de-entry cache, or simply the de-cache. The de-entry cache consists of three parts. First, lists of used de-entries linked off their associated inode via the ID-entry field of the inode object. Because a given inode can have multiple links, there might be multiple de-entry objects. Consequently, a list is used. A doubly linked list, or least recently used list of unused and negative de-entry objects. Okay, the list is inserted at the head such that entries towards the head of the list are newer than entries towards the tail. When the kernel must remove entries to reclaim memory, the entries are removed from the tail. Those are the oldest and presumably have the least chance of being used in the near future. So LRU cache basically is, let me see if I can. So an LRU cache in this case, since it is a doubly linked list, it's going to probably look something like this, where entries more recent is going to be here, more I guess recently used. Yeah, it's not about time, it's about used. Less used. And there's probably going to be like some sort of counter in all of these called used. Maybe it's just like 5 and then used. This is like 1 used. This is like 2. And this is like, this one is not really like, not a counter, but like not the number of times it's used, but like time. Okay, so that's like time. So whenever, let's say, this one gets used, it'll then be like 6, for example, and then this moves up to the top. So a hash table and hashing function used to quickly resolve a given path into an associated de-entry object. Okay, so these are all the parts. The hash table is represented by the de-entry hash table array. Each element is a pointer to a list of de-entries that hash the same value. The size of this array depends on the amount of physical RAM in the system. The actual hash value is determined by dhash. This enables file systems to provide a unique hashing function. Hash table lookup is performed via dlookup. If a matching de-entry object is found in the dcache, it is returned. On failure, null is returned. As an example, assume that you're editing a source file in your home directory. Home Dracula source thesunsucks.c. So these are all going to be different de-entry objects. So the root, home, Dracula source, and then the sunsucks.c. So each time this file is accessed, for example, when you first open it, later save it, and then compile it and so on, the VFS must follow each directory entry to resolve the full path. So basically root, home, Dracula source, and then finally the sunsucks.c. Okay. To avoid this time-consuming operation each time this path name is accessed, the VFS can first try to look up the path name in the de-entry cache. If the lookup succeeds, the required final de-entry object is obtained without serious effort. Okay, so, okay, it makes sense, cached. Conversely, if the de-entry is not in the de-entry cache, the VFS must manually resolve the path by walking the file system for each component of the path. So again, the thing to remember is that walking through the file system is initially expensive. That stuff eventually gets cached, so it's faster. So going through folders. After this task is completed, the kernel adds the de-entry objects to the cache or the dcache to speed up any future lookups. The dcache also provides the front end to an inode cache, the iCache. Inode objects that are associated with dentry objects are not freed because the dentry maintains a positive usage count over the inode. This enables dentry objects to pin inodes in memory. As long as the dentry is cached, the corresponding inodes are cached too. Consequently, when a path name lookup succeeds from cache, as in the previous example, the associated inodes are already cached in memory. Caching dentries and inodes is beneficial because file access exhibits both spatial and temporal locality. File access is temporal in that programs tend to access and reaccess the same files over and over. Thus, when a file is accessed, there is a high probability that caching the associated dentries and inodes will result in a cache hit in the near future. File access is spatial in that programs tend to access multiple files in the same directory. Okay? Thus, caching directory entries for one file have a high probability of a cache hit as a related file is likely manipulated next. So basically, anything that is, let's say, if you had a folder here, let's say a root folder, and then you'll have FA, and then you'll have many other files right here, and then maybe FB, folder B, more files here. So if you were to hit this file here, most likely these other files will also be cached too, because they are close to each other in terms of, I guess, spatial locality. Now, if you, let's say, access this file next, then this file is still cached, right? Because it's likely that you're going to access it again. Same thing for here and here. Well, of course here, but okay. Just reviewing for myself. Okay, so dentry operations. The dentry operation structure specifies the methods that the VFS invokes on directory entries on a given file system. The dentry operation structure is defined in linux/dcache.h. So here's a struct for all the dentry operations, and again, they exist as dops in dentry struct here. So there's a dopt right here. So struct dentry operations pointer, right? A pointer to that called dop, and that's just basically all the methods that you can invoke on the dentry. So the struct dentry pointers over here as the first arguments. That's, again, in object-oriented world, that would be equivalent to like the this pointer or this instance. So the methods are as follows. Okay, get ready, everybody. D-revalidate determines whether the given dentry object is valid. The VFS calls this function whenever it is preparing to use a dentry from the dcache. Most file systems set this method to null because their dentry objects in the dcache are always valid. Okay. Dhash creates a hash value from the given dentry. The VFS calls this function whenever it adds a dentry to the hash table. Dcompare, called by the VFS to compare two file names, name1 and name2. Okay, most file systems leave this at the VFS default, which is a simple string compare. For some file systems, such as FAT, a simple string compare is insufficient. The FAT file system is not case sensitive and therefore needs to implement a comparison function that disregards case. This function requires a dcache lock. Okay, delete, called by the VFS when the specified dentries object's dcount reaches 0. This function requires a dcache lock and the dcache entries dentries delock. Derelease, called by the VFS when the specified dentry is going to be freed. The default function does nothing. Void diput, called by the VFS when a dentry object loses its associated inode, say because the entry was deleted from the disk. By default, the VFS simply calls iput function to release the inode. If a file system overrides this function, it must also call IPut in addition to performing whatever file system specific work it requires. Cool. The file object. The final primary VFS object that we shall look at is the file object. The file object is used to represent a file opened by a process. When we think of the VFS from the perspective of user space, the file object is what readily comes to mind. Processes deal directly with files, not superblocks, inodes, or dentries. So those are like lower level abstractions. The user processes think in terms of files. So they don't care really about superblocks, inodes, or dentries. It is not surprising that the information in the file object is the most familiar. Data such as access mode and current offset, or that the file operations are familiar system calls such as read and write. The file object is the in-memory representation of an open file. The object, but not the physical file, is created in response to the open system call and destroyed in response to the closed system call. All these file-related calls are actually methods defined in the file operations table. Because multiple processes can open and manipulate a file at the same time, there can be multiple file objects in existence for the same file. The file object merely represents a process's view of an open file. That's why processes all get their own set of file descriptors. The object points back to the dentry, which in turn points back to the inode that actually represents the open file, so like the real file. So there can be many file objects for basically the same inode. There's only one inode. So the inode and dentry objects, of course, are unique. Yep. So the file object is represented by the struct file, type, and is defined in Linux/fs.h. Let's look at the structure, again with comments added to describe each entry. Struct file, again, all this stuff here. File operations table, which is basically the methods you can, and then this is the dentry, fpath. There should be like a pointer then, I guess, to the inode, but I guess you can access the inode from the dentry. Yeah. Okay. So similar to the dentry object, the file object does not actually correspond to any on-disk data. So no references to the real data on the disk with the file object. Therefore, no flag in the object represents whether the object is dirty and needs to be written back to disk. The file object does point to its associated dentry object via the fdentry pointer, and then the dentry in turn points to its associated inode, which reflects whether the file itself is dirty. So all this indirection here, if you want to access the inode, you have to go through the dentry to do that. Okay, so file operations. As with all the other VFS objects, the file operations table is quite important. The operations associated with the struct file are familiar system calls that form the basis of the standard Unix system calls. The file object methods are specified in file operations and defined in Linux/fs.h. Okay. So all the methods again, same thing. I think we probably just read this on our own, as always. Okay, so file systems can implement unique functions for. Good reminder here is that it's up to the file system to implement each one of these function pointers. Otherwise, there's going to be a default implementation provided in place of that. So file systems can implement unique functions for each of these operations, or they can use a generic method if one exists. The generic methods tend to work fine on normal Unix-based file systems. A file system is under no obligation to implement all these methods, although not implementing the basics is silly, and can simply set the method to null if not interested. Okay, so you should try to implement the basics. Here are the individual operations. LLC. updates the file pointer to the given offset. It is called via the LC system call. Reads count bytes from the given file at position offset in a buff. The file pointer is then updated. This function is called by the read system call. AIO read begins an asynchronous read of count bytes into buff of the file described in IOCB, IO callback probably. I guess kernel IO callback. This function is called by the AIO read system call. Asynchronous IO read. Size size T write. Okay, basically writes count bytes, the count bytes here from the buffer, okay, into the given file at the position offset. The file pointer is then updated. This function is called by the write system call. So these are all like more or less like more familiar. I just didn't realize there was like an AIO read and AIO write. That's pretty cool. Begins an asynchronous write of count bytes into buff of the file described in IOCB. This function is called by the AIO write system call. Reader returns the next directory in the directory listing. This function is called by the reader system call. Poll sleeps, waiting for activity on the given file. It is called by the poll system call. IOCTL sends a command and argument pair to a device. It is used when the file is an open device node. This function is called from the IOCTL system call. Callers must hold the BKL, which is the big kernel lock. Okay. Unlocked IOCTL implements the same functionality as IOCTL, but without needing to hold the BKL. The VFS calls unlocked IOCTL if it exists in lieu of IOCTL when user space invokes the IOCTL system call. Thus, file systems need implement only one, preferably unlocked IOCTL. Compact IOCTL implements a portable variant of IOCTL for use on 64-bit systems by 32-bit applications. This function is designed to be 32-bit safe even on 64-bit architectures, performing any necessary size conversions. New drivers should design their IOCTL commands such that all are portable and thus enable a compact IOCTL and unlocked IOCTL to point to the same function. Like unlocked IOCTL, compact IOCTL does not hold the big kernel lock. mmap, I've heard of this one. Memory maps the given file into the given address space and is called by the mmap system call. Open creates a new file object and links it to the corresponding inode object. It is called by the open system call. Flush, called by the VFS whenever the reference count of an open file decreases. Its purpose is file system dependent. Its purpose is file system dependent, meaning it depends on the file system to implement whatever they want with flush. Release, called by the VFS when the last remaining reference to the file is destroyed. For example, when the last process sharing a file descriptor calls close or exits. Its purpose is file system dependent. Okay, same thing. Fsync, called by the fsync system call to write all cache data for the file to disk. AIO fsync, called by the AIO fsync system call to write all cache data for the file associated with ILCB to disk. FAsync enables or disables signal notification of asynchronous IO. Lock manipulates a file lock on the given file. Readv, called by the readv system call to read from the given file and puts the results into the count buffers described by vector. Right there. The file offset is then incremented. WriteV, called by the WriteV system call to write from the count buffers described by the vector into the file specified by file. The file offset is then incremented. Send file, we're almost there. I think we're in S. Called by the send file system call to copy data from one file to another. It performs the copy entirely in the kernel and avoids an extraneous copy to user space. Okay. Send page, use to send data from one file to another, and then get unmapped areas, get unused address space to map the given file. Check flags, used used to check the validity of the flags passed to the FCNTL system call when the setfl command is given. As with many VFS operations, file systems need not implement the check flags function or method. Currently, only NFS does so. This function enables file systems to restrict set TF or SCTFL flags, otherwise enabled by the generic FCNTL function. In the case of NFS, combining OAppend and ODirect is not enabled. I have no clue what that means. FLOCK, used to implement the FLOCK system call, which provides advisory locking. Oh, is there more? Oh gosh, okay. So many IOCTLs. Not long ago, there existed only a single IOCTL method. Today, there are 3 methods. Unlocked IOCTL is the same as IOCTL, except that it is called without the big kernel lock, BKL. It is thus up to the author of that function to ensure proper synchronization. Because the BKL is a coarse-grained, inefficient lock, drivers should implement the unlocked IOCTL and not IOCTL. Compat IOCTL is also called without the BKL, but its purpose is to provide a 32-bit compatible IOCTL method for 64-bit systems. So hence the compat. How you implement it depends on your existing IOCTL commands. Older drivers with implicitly sized types such as long should implement a compat IOCTL method that works appropriately with 32-bit applications. This generally means translating the 32-bit values to the appropriate types for the 64-bit kernel. New drivers that have the luxury of designing their IOCTL commands from scratch should ensure all their arguments and data are explicitly sized, save for 32-bit apps on a 32-bit system, 32-bit apps on a 64-bit systems, and 64-bit apps on a 64-bit system. These drivers can then point the compat IOCTL function pointer at the same function as unlocked IOCTL. Okay, so data structures associated with file systems. In addition to the fundamental VFS objects, the kernel uses other standard data structures to manage data related to file systems. The first object is used to describe a specific variant of a file system, such as ext3, ext4, or UDF. The second data structure describes a mounted instance of a file system. Okay? Because Linux supports many different file systems, the kernel must have a special structure for describing the capabilities and behavior of each file system. Oh, I would have assumed that would have been in like the superblock. The file system type structure defined in Linux/FS accomplishes this. So this is the information about the current file system itself for the name. Oh yeah, here's the superblock. So I guess more stuff about it is in the superblock. Terminate access is superblock. The module owning the file system, basically the thing that created, mounted it. Yeah, cool. Oh boy. Okay, let's see. The getSB function reads a superblock from the disk and populates the superblock object when the file system is loaded. The remaining functions describe the file system's properties. There is only one file system type per file system, regardless of how many instances of the file system are mounted on the disk. So only one of these things, or whether the file system is even mounted at all. Things get more interesting when the file system is actually mounted, at which point the VFS mount structure is created. This structure represents a specific instance of a file system, in other words, a mount point. The VFS mount structure is defined in linux/mount.h. Here it is. Okay, mount points. This is what a mount point looks like. Lots of stuff. Okay. So basically, the complicated part of maintaining the list of all mount points is the relation between the file system and all other mount points. The various linked lists in VFS mount keep track of this information. All of this. Yeah, all of these list heads right here. Okay. So the VFS mount structure also stores the flags. If any specified on mount in the MNT flags field. Table 13.1 is a list of the standard mount flags. Sure. No exec is useful, I guess. It forbids execution of binaries on this file system. Okay. These flags are most useful on removable devices that the administrator does not trust. They are defined in linux/mount.h along with other lesser used flags. All right, so data structures associated with the process. So file system data structures associated with each and every individual process. Each process on the system has its own list of open files, root file system, current working directory, mount points, and so on. 3 data structures tie together the VFS layer and the processes on the file system. File struct, FS struct, and namespace. The file struct is defined in linux/fd table, file descriptor table.h. This table's address is pointed to by the files entry in the processor descriptor. All per process information about open files and file descriptors is contained therein. Here it is with the comments. So, okay, it's just a table. Okay, pointer to the other FD table. Base FD table. The base files array, so all the open files. Okay. The array FD array, so right here, points to the list of open file objects because number open default is equal to bits per long, which is 64 on the 64-bit architecture. This includes room for 64 file objects. Okay, so max is 64 here. If a process opens more than 64 file objects, the kernel allocates a new array and points the FDT pointer. Oh, okay. Add it. So this is going to be, the pointer to the other FD table. So the extended version after you hit your limit. Okay. In this fashion, access to a reasonable number of file objects is quick, taking place in a static array. If a process opens an abnormal number of files, the kernel can create a new array. If the majority of processes on the system opens more than 64 files for optimal performance, the administrator can increase the number of open default preprocessor macro to match. Okay, so the second process-related structure is FS struct, which contains file system information related to a process and is pointed at by the FS field in the process descriptor. The structure is defined in linux/fsstruct.h. Here it is with comments. So users, lock, umask, okay, root directory, and the working directory. Sure. So the structure holds the current working directory and the root directory of the current process. It's good to know. The third and final structure is a namespace structure, which is defined in linux/mnt namespace.h and is pointed by the mount namespace field in the process descriptor. Per process, namespaces were added to the 2.4 Linux kernel. They enable each process to have a unique view of the mounted file systems on the system, not just a unique root directory, but an entirely unique file system hierarchy. Here is the structure with the usual comments. Sure. Anyway, I guess we're here. List of mount points again. All right. The list member specifies a doubly linked list of the mounted file systems that make up the namespace. These data structures are linked from each process descriptor. For most processes, the process descriptor points to unique file structs and FS struct structures. Okay, so processes have their own file structs and FS structures. For processes created with the clone flag, clone files, or clone FS, however, these structures are shared. Consequently, multiple process descriptors might point to the same file struct or FS struct structure. The count member of each structure provides a reference count to prevent destruction while a process is still using the same structure. Okay, the namespace structure works the other way around. By default, all processes share the same namespace. Oh, interesting. That is, they all see the same file system hierarchy from the same mount table. Only when the clone new NS flag is specified during clone is the process given a unique copy of the namespace structure. Is this like chroot? Because most processes do not provide this flag, all the processes inherit their parents' namespaces. Consequently, on many systems, there is only one namespace, although the functionality is but a single clone UNS flag anyway. Alright, finally. It wasn't that long, it's just not very interactive. It's just reading off a list. Conclusion. Linux supports a wide range of file systems, from native file systems such as ext3 and ext4 to networked file systems such as NFS and Coda. More than 60 file systems alone in the official kernel. The VFS layer provides these disparate file systems with both a framework for their implementation and an interface for working with the standard system calls. The VFS layer thus both makes it clean to implement new file systems in Linux and enables those file systems to automatically interoperate via the standard Unix system calls. This chapter described the purpose of the VFS and discussed its various data structures, including the all-important inode, dentry, and superblock objects. Chapter 14, the block I/O layer, discusses how data physically ends up in the file system. Okay, I think this is what I was looking for. Okay. Next time.